So let's look at another example. This is again another product mix example, and it's for Galaxy Industries. It's a toy company that produces two space-age water guns, a space ray and a phaser. We're producing them in lot sizes of 12, so a dozen, and we are making it exclusively from a special plastic compound. Each week, Galaxy Industries has 1,200 pounds of the plastic compound and 40 hours of production labor available. There are some strategic decisions that have been kind of handed down to us from our bosses, the powers that be. One of them is limit total production to 800 dozen or lots each week. And then the other one is weekly production of space rays cannot exceed phasers by more than 450 dozen. So that one is kind of trying to put some kind of ratio or mix of what the upper level people think is a good way to market the products, perhaps, right? So that's not an unusual thing in the real world. So we could that's why we're looking at it here. Space rays make a profit of $8 per dozen and take 2 pounds of plastic and 3 minutes of manufacturing time. Phasers make a profit of $5 a dozen and take 1 pound of plastic and 4 minutes of manufacturing time. Our goal now is to formulate the problem. So we're going to do something similar to what we did before. We have our outline here. We say let and then define the decision variables. So this time let's be a little better than just x1 and x2. All right, let's say let S equal the number of lots, in our case this is dozen, of space rays to produce or make next week. So it's just a coincidence here that both of our product mix examples are looking at a weekly production cycle. And then P for the other one, number of lots, that's dozen, of phasers to make next week. Right. And I said we're maximizing, and it was given to us as profit, so we're maximizing total profit. Total profit, we made $8 from each lot of space rays and $5 from each phaser. And then we need to come up with our constraints, subject to a bunch of constraints. So the first one we could look at is plastic. We had a total of 1,200 pounds of plastic, so this is pounds of plastic. And we want to stay under that. And it takes 2 pounds for each space ray and only 1 pound for each phaser, so I'm not going to put the 1 in front of it this time. And then the next thing we had was total labor. We had 40 hours, and it took 3 minutes for space rays and 4 minutes for phasers. So we have minutes versus hours, so we can either convert the minutes, 3 and 4, to an hour, which would be fractions, or we can convert the 40 hours to minutes. I prefer to do the 40 hours to minutes, so 40 times 60 gives me 2,400. And then over here we need to make sure we say this is total labor in minutes. All right? And it takes 3 minutes for each lot of space rays and 4 minutes for each lot of phasers that we do. So those were the 2 resource constraints that we need to deal with. The other thing we have to deal with are those strategic level decisions that were handed down to us. The first one said limit the overall production to 800 units. So we need 800, and we need to stay under that. And this says total production limit or maximum, whatever you want to call it. And that's just simply adding up how many lots of space rays we did and how many lots of phasors we did. So S plus P. Right? Then we need to do the other one, which was a little more complicated. It said we want to make sure that the weekly production of space rays cannot exceed phasors by more than 450 dozen. So probably the easiest way to do this is to just try to write it as it sounds. And I'm going to write this in blue. I think that'll work. So for this we're going to say space rays cannot exceed, so that means it has to be less than or equal to, phasors, so we write down the symbol for phasors, by more than 450. So we have a plus 450. So I think that takes care of that constraint, but notice it's different than the other ones we've done so far. This time we have variables on both the left-hand side and the right-hand side. We want to put it in what's called standard form. So we put all the variables on the left-hand side and just have a constant on the right-hand side. This is also nice because when we do this and we try to put it into Excel to solve it later, it makes our life a little bit easier. So I simply need to rearrange terms. So what that means is I need to take this P and move it over here by subtracting P from both sides. So it puts the P over here, keeps the 450 by itself. So let me rewrite it up here in black. So we have S minus P, because I subtracted P from both sides, less than or equal to 450. And we'll call this one, what's a good thing? Maybe production mix or ratio, strategic initiative. That's a good word. I just can't write it today for some reason. Initiative. I might get it. That's kind of close. You can almost read my handwriting. Right. So we've got the two resource constraints. The one's on plastic, the one's on labor minutes in this case. And we got the two strategic initiatives, the total production limit and also the ratio. And then the other thing we need is non-negativity. This time I'm going to put it on a single line, S, and this is a comma, P greater than or equal to 0, and it's non-negativity. So the difference between this one and our last example, is that we have 4 structural constraints and 2 lower bounds, right? So, this one, those are the same, right? I've just rearranged it, right? So now we have a second example. It's still product mix. We'll still only have 2 variables, but now we have more constraints.